Now we continue with our lessons on motion, and this time around I'm looking at the dynamics of motion. Dynamics is the study of a body in motion under the action of forces. It is divided into two broad headings, kinematics and kinetics. Kinematics studies the motion of a body without reference to the force producing such a motion. And it considers just the geometry of motion, which includes distance, displacement, speed, velocity, and acceleration. In my previous videos, I've taken time to do some justice to this aspect of dynamics, which is kinematics. Now, kinetics, on the other hand, is the study of the forces that produces motion. It is the study of the force producing motion. It also considers the energy responsible for a given motion. Of course, a force is any action capable of accelerating an object, and it's a vector quantity. The application of force to a body may change the direction of motion of such a body. It can change the state of rest of the body. And then in these video lessons, I'll concentrate on this kinetics, which has to do with the force that is responsible for motion. And before we delve into that, we're going to consider the three laws Newton's gave to us. We call them the Newton's laws of motion. Now, the first law of motion is the law of inertia. It states that a body at rest will remain at rest, and a body in motion will remain in motion with a constant speed along a straight line, unless a resultant force, unless an unbalanced force, unless an external force acts on it. Now, the tendency of a body to remain in the state of rest or in the state of uniform motion along a straight line is called inertia of the body. And there are three types of inertia. We have the inertia of rest. Now, when it comes to inertia of rest, we are talking about a body that is placed on a surface. It remains there as long as we want that body to remain there until the force acts on it. We have the inertia of motion. A body will continue at the same speed until the force acts on it. A body will continue along a straight line to move with a constant speed if no resultant force acts on it. So if I need to accelerate the body, I need to apply resultant force to it, whether to accelerate it or to decelerate it, or to slow it down. We also have the inertia of direction. A body continues in a particular direction until a resultant force acts on it. Okay, so this tendency of a body to remain in the state of rest or in the state of motion along a straight line unless a force acts on it is called the inertia of the body. And Newton's first law is otherwise referred to as the law of inertia. Now let's see some of the examples of Newton's first law of motion in nature. Naturally speaking, we must have seen this before happened. Now, a driver that suddenly applies the brakes to his vehicle, you understand that when that is done, we feel this momentary pull in the forward direction, which means that due to the nature of motion, our body wants to continue to move. Hence the reason why we jerk forward, we move forward when the brakes are suddenly applied to the vehicle that we are in. An object on a plane surface remains on that surface as long as we want it, unless a resultant force acts on it to change its shape, to change the size, or to change the position of such an object. Now, a marathon runner, a sprinter, whenever they come to the finishing line, they do not stop immediately. They keep running for a while. Why? Because of the nature of motion. Their body just wants to continue to move until it takes some time to come to rest. Now, a car crashes into another stationary car behind it. What's the effect of that? The effect of a driver in the stationary car, where the driver is already sitting there in the stationary car, he's not moving the car, and the car comes from behind and crashes into it. What happens? Now, his car is suddenly knocked forward, and the body is pushed forward by the seats. His head stays still on his state of rest. For this reason, neck injuries are common in such an accident. How about a ball rolling on the ground? Now, when a ball rolls on the ground, if you continue to roll on the ground according to Newton's first law, but we'll notice that this ball is soon brought to rest, soon come to rest. Why is it so? Because of the external forces acting like frictional force, which opposes the motion of the body and eventually brings it to rest. And how about a ball that is thrown into outer space like a rocket? Now, this body tends to move in a direction towards infinity. This is because outer space lacks air, lacks atmosphere, and also lacks the force of gravity. Hence, a body does not receive any resistance to motion. It continues to exhibit this motion until it is brought to rest by a celestial body, or when it enters the gravitational field of a planetary body out there in the outer space. Then the body is made to change its direction or change its path of motion. Now, it's very important to note here that when the body is moving with a uniform speed in a straight line, it needs no force to keep it in motion, provided there are no external opposing forces acting on the body. Because these forces tends to decelerate the motion of this body. That's why when a rocket is launched into outer space, it will continue to its destination, perhaps the moon, without any further force. Its speed will not increase. The speed will not decrease until it is acted upon by the attraction of some other planet that, if eventually the rocket enters into a different planet, is compelled to change its path by the gravitational field of that planet. Now, a limitation of Newton's first law of motion is that the law does not provide us an equation, a formula for calculating that external force that is needed to change the direction of motion of a body, to accelerate a body, or to decelerate a body. So we learn from Newton's first law, we can deduce from Newton's first law that a force is needed to accelerate a body, to decelerate a body, and also to change the direction of motion of a body. And this will lead me to Newton's second law of motion. Now look at Newton's second law of motion. Newton's second law of motion states that the applied force F is directly proportional to the rate of change of momentum and takes place in the direction in which the force acts. That is, Newton's second law by extension means that the rate of change of the momentum of a body is directly proportional to the applied force, and then it takes place in the direction in which the force acts. It's Newton's second law of motion. Now, F is the force. Is directly proportional to the rate of change of momentum. You can say change of momentum of the body divided by time taken for the change. Okay, now momentum change of a body, I can use this symbol to denote momentum change. This symbol of momentum over time, T, and we'll say that is directly proportional to the force applied. Now, momentum has been defined as the product of mass and velocity of a body, meaning that a body in motion has momentum. It is the motion of a mass of a body in motion, that's momentum. So it's the product of mass of a body and its velocity. Now, momentum change means that there must be an initial momentum and also a final momentum. So it is the final momentum minus the initial momentum that gives momentum change, because this is the final velocity, this is the initial velocity u. So that gives the change in momentum of the body. So I can come here and write F is proportional to mv, final momentum, minus initial momentum divided by time taken for the change. Now, if I remove this sign and introduce my equality sign, I have F equals K into final momentum minus initial over time taken. Now, we have to factor out the mass. Mass is common to both terms of this expression. I have V minus U divided by T. And we know that from kinematics, that final velocity minus initial velocity over time, we define this as acceleration of the body. So then we write F now equals Km times A. So that gives us the equation F equals mass times acceleration. Now we have to define the constant K. K is defined in such a way that the value of 1 Newton, a force of 1 Newton, is used to define the value of K. 1 Newton is that force that gives an acceleration, the force that produces an acceleration of 1 meter per second squared to a body of 1 kilogram. So that has been defined as 1 Newton. So the force that gives an acceleration of 1 meter per second squared to a body of 1 kilogram is defined as 1 Newton, meaning that when F is 1, it means that M is 1 and A is 1. So when we substitute for M, A, and F, we'll get our K as equal to 1. So that substituting back into the equation, I have F equals M times A. Okay, so that is one of the equations of the force acting, the applied force that is applied to a body according to Newton's second law of motion. If I come back to this expression, F equals K into mv minus mu over t, I'm going to have that, and then we also take K as 1 here, which means F equals mv minus mu over t. This equation defines what force is. That the force applied to a body is defined as the rate of change of momentum of that body. If the momentum of that body changes, it means that a force is actually applied to that body. If there's no change in the momentum of the body, if the momentum of a body is constant, momentum of a body does not change, is constant, it means the force applied will be what? If there's momentum change, the force applied will not be constant, it will be zero. So for we to say that a force has acted on a body, the body's momentum must change. The change in momentum shows that a force is applied to the body, and this force can either accelerate the body or decelerate the body or change the direction of motion of the body. Okay, so now let's come back to this expression F equals m times A. Now, which means here that keeping the mass of a body constant, the force applied here is directly proportional to the acceleration of a body. It means that if you must provide or impact a greater acceleration to a body, the force applied must be greater. So the greater the acceleration, the greater the applied force, keeping the mass of the body constant. Okay, so if for the same acceleration, and we need to vary the force applied to the mass, which means that if I need to create or to impact greater acceleration to two different masses, the one with the higher mass will need a greater force. Just like you have a car and a truck. A truck is by far heavier, weightier than a car. So if the car has a mass of 800 kilograms, for instance, and this truck has a mass of 2000 kilograms, of course, if I want to give them the same acceleration, maybe 1 meter per second squared, I'll need a greater force to apply to the truck than to apply to the car. So the greater the mass for the same acceleration, the greater the force that will be needed to impact that acceleration. And then the variation of F and the acceleration, keeping mass constant. How does F vary with this? It's a straight line graph, and the slope of this graph represents the mass of the body. So if acceleration is plotted against a force, or force plotted against acceleration, we have the slope as mass. Or when we plot the force applied to a body with the varying mass, how does force vary with mass? It varies linearly, straight line graph, and the slope represents acceleration of the mass, acceleration impacted to the mass. Now, lastly on this, the from this equation, F equals ma. Now, this force most times is called one, the resultant force. We can call that F, the resultant force. It can also be called the net force. Of course, resultant force is the result, when two forces are combined. The results obtained when forces are combined, when vectors are combined, we have a result. The result is called the resultant vector. Recall that the way we combine two vectors is quite different from the way we combine two scalar quantities, because when we combine two vectors, we must take into account the direction of the vectors as well. So F is also known as the resultant force, is the net force. We can call F the accelerating force, the force that produces the acceleration A. And most times this A could mean deceleration. In that case, F becomes the decelerating force, the force that produces the deceleration A. So you can see the several names given to F. It's also called the resultant force or the net force, or the accelerating force, or the decelerating force in the case where it causes a deceleration. The next video will solve problems on this Newton's second law of motion.